Hello, and welcome to Quadratic Functions. My name is Tuesday Johnson. Here's an introduction to a concept. Hit the wrong button. So let's look at quadratic in form. A quadratic function of the variable x is a function that can be written in the form f of x equals ax squared plus bx plus c. You may have also seen this in the form as y equals ax squared plus bx plus c, the function notation, the equation notation, and that's why we say it's quadratic in form, because the right-hand side is the same in both cases. And in both cases, a, b, and c are fixed numbers. So we'll have numbers here where a cannot be 0. What happens? If a is equal to 0, 0 times x squared is 0, and we're just left with a linear function. So this condition, a cannot be 0, is specific to the items that we call quadratic functions. All right. Graphs. Once we have an equation, we're going to want to look at the graph. For the function f of x equals ax squared plus bx plus c, where a is not equal to 0, we know that the graph of every quadratic function forms a parabola. If a is greater than 0, the graph opens upward, or concave up. Whereas if a is less than 0, the graph opens downward, or we say that it's concave down. The vertex will be the highest or the lowest point on a parabola, right, depending on whether it opens up or down. The x-coordinate of the vertex is given by the formula that x is equal to negative b divided by 2 times a. Negative b over 2 times a. The y-coordinate of the vertex is given by, well, it's just take that x answer and substitute it in and find your y value. So just evaluate the function at the first value. And here we have the vertex is at the top of the graph, the highest point. More on quadratic graphs. There are x-intercepts sometimes, right? Not always, but they occur where f of x is equal to 0. To solve 0 equals ax squared plus bx plus c for x, we could use factoring, or we could use the quadratic formula. So if you want to find x-intercepts, use the quadratic formula after you get it in standard form. I'm going to show you a method that doesn't really use the x-intercepts for graphing, however. So make sure you understand this concept without the examples that are going to flow. If the discriminant, right, this thing under the radical, the radicand, it's going to tell us how many x-intercepts there will be. So if b squared minus 4ac is greater than 0, there will be 2 real valued x-intercepts. So we'll see the graph cross the x-axis twice. If b squared minus 4ac is equal to 0, there will be 1 real valued x-intercept. We'll only see the parabola kind of bounce off of the x-axis. And if b squared minus 4ac is less than 0, there will be no real valued x-intercepts. So the parabola won't touch the x-axis at all. A couple more items on the quadratic graphs. These are going to be important points such as the y-intercept. The y-intercept of the graph is the point where x is equal to 0. For a quadratic, if the x value is 0, the first 2 terms go away and we're left with c. So that gives us the point 0, c as the y-intercept of a quadratic graph. This is going to be an easy point for us to find in our examples. Now, the graph of a quadratic function is symmetric about the vertical line through the vertex. All right, so it's like this is a mirror. It's called the axis of symmetry. This is given by the equation. It's a vertical line, right? So it's x equals, an equation always has something on the left, an equal sign, something on the right. So it's a vertical line, x equals negative b over 2a. And what we're going to do is we're going to find a symmetric point here. Let me see if I can find the right button. That has the same height as our y value. And notice that these x values are exactly the same distance apart, right? They're the same distance from the axis of symmetry. So we're going to use this to help us find a vertex, the y-intercept, and a point symmetric to the y-intercept. Okay, so let's sketch the given quadratic function. F of x equals 2x squared plus 3x plus 1. Now, we know that this graph faces upward since the 2 in front of the x squared is positive. We know that the y-intercept is at the point 0, 1 because 1 is the c value of our function. To find the vertex, we'll use x equals negative b over 2a. In this case, our b value is 3, so we'll have negative 3 over 2 times, and in place of a, we have a 2. 2 times 2 is 4, so our x value of the vertex is negative 3/4. To find the y value, we take our equation and replace x with a negative 3/4. Notice the use of parentheses. Parentheses are your friends. They'll help you make sure all your calculations stay in the correct order. And when we evaluate this, however you choose to, by hand or by calculator, you'll end up with a negative 1/8. So the point negative 3/4, comma negative 1/8, is the vertex or turning point of this graph. So we have a point 0, 1 that has a height of 1. This point is negative 3/4, or 3/4 of a unit to the left of the y-intercept. So our symmetric point is going to go further left. It's going to double the x value of the vertex. So if we double negative 3/4, we'll have a negative 3/2, and we'll use the y value of the y-intercept. All right, if we look at that, 0, 1 is our y-intercept. Negative 3/4, negative 1/8 is our vertex. And the distance from 0, 1 to the axis of symmetry is 3/4. 3/4 to the left, right? The negative is telling us a direction. So we go another 3/4 to the left, which is double the x value of the vertex, to get our symmetric point of the same height as the y-intercept. All right, another one. That was so much fun. So f of x equals x squared plus 6x plus 9. To determine if the function opens up or down, we look at the coefficient of x squared. 1 is positive, so it opens upward. Our y-intercept comes from the constant term. It's always, the y-intercept always has an x value of 0. And the y value is the constant 9. Our vertex is negative b over 2a. And here I did it slightly different. I did different use of the negative just to show you diversity. Negative b over 2 times a. If the number is not written, it's assumed to be a 1 in math. 2 times 1 is 2. 6 divided by 2 is 3. I'll have negative 3. In order to find the y value, I'll substitute negative 3 everywhere I see an x. Keep in mind x is squared, so I have to make sure the whole negative 3 gets squared. So use parentheses. Parentheses will be kind to you. The x value is negative 3. The y value is 0. And our symmetric point, we had the same distance from the vertex as the y-intercept. This is 3 units away. 3 units on the other side will give us a negative 6. Same height as the y-intercept because that's the one that we are mirroring. And we see our graph here with the y-intercept of 0, 9, vertex of negative 3, 0, and a symmetric point of negative 6, 9. Notice we didn't need x-intercepts in order to get an accurate graph. Last example. F of x equals negative x squared plus 2x minus 5. This graph opens downward due to the negative 1 coefficient. The y-intercept is at 0, negative 5. And the vertex can be found as negative b divided by 2 times a. So negative 2 divided by 2 times negative 1. 2 divided by negative 2 with another negative going on makes a 1. And then evaluate. This one is very specific and different from the previous example. In the previous example, the negative 3 was being squared. Here, the negative is not squared. Make sure it's only the x value, 1, that is inside the square. Make good use of your parentheses. Your calculator is only going to do the operations you tell it to. So we'll have 1, negative 4 as the point of the vertex. Our symmetric point will double our x values, twice the distance away. From distance of 0 to 1 from y-intercept to vertex, so it must be from 1 to 2 to the symmetric point, same height. And a look at our graph. Yeah, we're kind of rolling downhill at this point in the semester. You could tell I was picking up speed in this application, but I don't want it to go too long. You're not going to watch it. So if you need to, pause, look at it, make sure you understand along the way where all of these values came from. Thank you so much for watching. Have a great day.